parameter that in this case must be dimension of seconds, because derivative is with respect to time, and here sigma must be measured in length. We must change this operator by this operator. The question is, what is sigma? In this year, sigma was valued by a scientific from some university from experimental data. Okay, this is our important contribution to fractional calculus. Now, some researchers use this change operator. So if we take into account this operator, we have the following. Yes. Okay. Okay, we consider electromagnetic waves when G is equal to 0 and rho 0. We have the following. Very simple model.
I have a stupid question. When you have in the standard electrodynamics, when you have 37 and 38, you also have continuity equation, right? For the currents, the densities, and the conductivity, right?
Right.
Okay.
Okay.
And does this change into fractional calculus changes the continuity equations?
Yes, so we will change operator.
Everything.
Okay. Yes.
Thank you.
Okay.
And the factor gamma, I think, is the same for.
No. This is yes. This is the same because dimension of time.
So you're only changing here the time derivative by
time derivative. The space. We have only fractional derivative in time, but not in space.
But the continuity equation has the space part and time part too, I think, if I remember, right?
You're right. We do this in two parts. First, fractionalize only time. After that, second part, fractionalize only space. Okay?
So that here you interchange the conventional derivative of time by the fractional one, and by adding this sigma parameter,
Yes.
that you tell us that has presently measured in the laboratory.
Yes.
Because this has the appropriate units in order to have all the derivatives with time units. Yeah?
Yes. Okay. We reduced our problem to some physics. Reduce problem, complete problem to easy problem. Okay. We can write these two equations in compact form with zeta, and we consider a polarized electromagnetic wave. Then we have the following condition, and we put as a solution the following. Okay. Put in here, we obtain the following fractional equation. This we change by here. Okay. This is a fundamental frequency. Sigma is the sigma parameter which is introduced. Omega is B is the speed of electromagnetic wave in the medium. then we can write the above equation in this form. Applying the Laplace transform and the Laplace transform or the computer fractional derivative, we obtain the following solution, where this is the function, the Mittag-Leffler function.
One parameter.
One parameter, yes. So we have the following solution. So if we put gamma is equal 1, we have the ordinary monochromatic way, plain way. Okay, from here. Above was above we got the particular function of the Mittag-Leffler. Okay, we have this solution. When gamma is equal 1/2, we get the following. The periodicity on time is lost. Only periodicity in x. If we fractionalize the derivative in the equations, we losses periodicity in time. Similar will be if we take the fractional space and we keep the time derivative.
I have a question. This increases in time. This depends on time.
It seems that there is a minus on this.
Yeah. Yes. From here. Yes, it might be.
It could
minus.
be. Yeah,
Yes.
okay.
Maybe my mistake. In the yes. Yeah. Yes, minus. Pardon?
In 46, where you have this periodic waving, plane waving in x, 46, I think, the top, yes. Then with that left function, how does it behaves for different values of gamma? Is this a decreasing function? Or
Yes, decreasing. The gamma function, the gamma function, no. The Mittag-Leffler function decreases quickly, is exponential, but before some time with the potential function, negative potential function. And from one order gamma we have it. From another we have it. I have difficulty with English.
Don't worry.
No.
Recall that the official language here is bad English.
Okay. 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 Thank you. More question? No. Because I have some questions.
You can put.
Yeah. Some. Yes, I have a question for the public after.
Yes.
Okay. Another here we fractionalize the space and keep the fraction, the time derivative ordinary. Here. The solution is similar. Similar. Okay. This is the solution. And then here. This is here. I think the two problems. Okay, I will see what.
No, this one is nice, because this one also it's moving forward.
In time. Okay.
actually it's moving
Yeah.
backward,
Yeah.
backward in
Yeah.
time and decaying
Yeah.
in space.
He is correct. He is correct. Yes. Okay, and this is the solution. This is the solution. In the particular cases, we have this. Okay. In conclusion, a consistent fractional differential equation for the electromagnetic waves are obtained. This was by introducing a parameter sigma with dimension of seconds or length. Two types of the fractional equation have been examined separately: the fractional time derivative and the spatial fractional derivative. Separated. It was shown that in the first case, the periodicity with respect to time t is broken, and the wave behaves like a wave with the time decay amplitude. In the second case, the periodicity with respect to space x is broken, and the wave behaves like a wave spatially decaying amplitude e moving rapidly. It is interesting, I think, that to see a fractional derivative space together with fractional derivative time, fractional derivative, and different other beta, alpha, for example, alpha in space or beta in time, and to see some behaviors. This is example. This model we can apply to some problems in maybe in optics and I don't know. I think that there are very problems we can apply this. Okay, this is here is some reference. Some Bogdan Mielnik, etc. Quickly, rápido.
Could you go one back, please? Just one. It was too fast for me. Could you go one back?
One slide.
One slide back. Thank you so much.
Plenty time of questions and comments. You want? Yes, this is because in your solutions you completely lost periodicity, either in X or in time. So this is modeling basically evanescent waves either on space and on time. But I wonder if there is any possibility that the periodicity is not lost. So if you keep a factor which is harmonic and some factor which is decaying envelopes of the function in order to model some kind of leakage of absorption of the waves.
If we can model, I think that yes, I think that this is a part which we can to consider, because we work in this line, but we keep it and we continue working in another line of application of fractional calculus. But in this year, no, in the next year, we will to regresar,
Go back.
go back to search this problem.
I really like this idea of just taking the potential vector potential scalar potential, sorry, the vector potential and scalar potential, and just trying to fractionize either space or time to get into this exponential linear function. And it's super nice. But now, have you ever thought like, if you map this back into the whole integral differential system, what type of material would I need to get this?
Sorry, I don't know what material, but I think that we can do it.
But you don't have a clue what real physical object material?
No.
Will be a meta.
Will be very interesting to do a realistic experiment. Yes.
And also,
In general, this kind of laws appear, for instance, if you have
no, the
dissipative systems.
the type of the functions that he gets, they're amazing because either you have an evanescent wave or you have a decaying wave on time, a periodic one. But my skin is tickling because, for example, if I go for this, so I need a method, right? So in a method, I need to fulfill my continuity equations, and my continuity equations give me integral differential properties that I have to fulfill on the boundaries and everything. And I have this feeling that introducing the fractional calculus is not clear to me at first hand that all the boundary conditions required due to continuity, due to the continuity equation, to the boundary conditions of the materials and everything should be fulfilled at first hand. But the solutions are amazing because you have something that decays as an evanescent one and something that decays as in time. But then it's like,
Yes.
it's just matching.
In general, it depends. For instance, Juan told us about Maxwell equations. Fernando is going to talk in the next.
Question for Fernando.
Differential equations. No, let me finish. Differential equations. And the main difference with fractional calculus in general is that all you know about conventional calculus doesn't work. In particular, there is not in general a superposition principle, for instance, and the boundary conditions are not general. You cannot establish a general fractional differential problem with specific boundary conditions. The boundary conditions depend in every case.
But this is electromagnetic field. So you can test it on the lab. In principle. So I understand that fractional calculus is quite malleable and it's not like a super standard set of things. But any of this should be able, if feasible, to describe a physical system, should be able to be mapped into that.
We hope that. Yes.
I think that okay, because in this model there are no boundaries, so I think that the boundary conditions rolling here. But I think that okay, naturally there are boundaries.
No. The point is that by the type of solutions in his picture, it behaves as an infinite homogeneous material.
Yes.
But the type of solutions that he finds, most probably this is some type of mapping of a bounded type of material where you have losses, where you have and things, and then by some mapping it's translated into this homogeneous infinite cycle.
The speaker is there.
You can continue.
Sorry.
Okay, the problem we can see after.
Yes, of course.
Yes, but to finish and to conclude, what you are looking for is that, I repeat, this kind of behavior concerning the
I think he make it clear what he's looking for. You don't need to put that this way. I can get his point.
Fernando.
I have a question. In the transparency, before you put the expressions 46, 47.
46.
Yes. The transparency before.
previous.
Yes. it is not clear for me how. Well, I think that there is some term missing there, because when one solves that differential, that fractional differential equation, one obtains two terms. One, well, the first is the Mittag-Leffler term that is there, uniparametric, and there is another term that is missing there, that has the transparent the 45. The term that involves a Mittag-Leffler function with two parameters, alpha and alpha plus 1.
No. This is maybe how we define the fractional order in the.
No, yes. Well,
because I can define another here. I can define here. We can define, for example, gamma plus 1.
No, I understand.
Okay.
Yes, the fractional order in the transparency before is 2 gamma, and gamma goes from 0 to 1.
Yes.
Well, when one solves this fractional differential equation, there is another term there, a term that is another Mittag-Leffler function that has 2 parameters. In this case, the parameter should be gamma.
No, maybe 2 gamma, 1. We can write only 2 gamma.
Yes, because well, if you want to recover the conventional results with the well, yes, one recovers the cosine function there, but there is still missing the sine function. In the previous slide, there is still missing the term that goes to the sine function when one uses the Newtonian derivative. It's because well, that is the equation of the fractional oscillator. When we take
from here, we can obtain the fractional oscillator behavior.
Yes, but well, I think that there is still missing some term there.
No. Okay, so we can to continue this discussion after.
More questions?
So can you show the wave equations for the vector potential and for the scalar potential? The wave equations. Yeah.
Wait. No. Here?
No, the other ones.
We solved these equations.
Yeah, so only the homogeneous. So infinite medium.
Yeah.
Nevertheless, so you have the material electromagnetic parameters epsilon and mu, and you have also another parameter which is sigma that you add by hand.
Sigma
So
by hand.
this sigma looks again like a material parameter.
No.
It's clear.
Okay.
So it can be, it's not a, let's say it's not a common electromagnetic material. It has an extra material parameter, electromagnetic material parameter. So you could relate to what from deriving just to Hamilton of the material.
It's interesting that we can to put sigma. In this case, sigma is measuring seconds. We came to do a relation gamma. Gamma is equal to sigma to a period.
I also agree with the observation.
With periods, period on and change the esconder la sigma. See? Okay.
More questions or comments? I have one. Well, I understand that the reason to choose some definition of the fractional derivative is related to the system that you are studying. So there are a reason to choose Caputo and another one. Fractional definition.
There are some definition of fractional derivative. Caputo, Remaleville, Ratagano Mariano, Caputo Fabricio, that I don't present here. The reason was that in the Laplace transform or derivative of Caputo, we have a condition, ordinary condition. And in the case of Riemann-Liouville, we have fractional condition.
And you obtain different results if you choose the other definition?
Results very, very likely, similar. Right.
Another question or comment? Please.
For example, you can pass your equations to Fourier space.
Yes.
Your
Okay.
variable. That means, in some sense, transform it into an ordinary differential equation and see what's going on.
We transform in the fractional
Because
space.
it's not very clear what happens with the fractional equations. So you just have to go to the, let's say, to a certain Fourier space and work there. And it's precisely what.
Now, to pass to fractional Fourier space, we take from here.
Because it looks like a scale.
We apply the fractional Fourier transform.
Yeah.
Because there is fractional Fourier transform.
For example.
Questions? There are time yet. Let's thank the speaker again.